Hello there. In this Fundamentals webcast, we will be discussing line structures. Line structures are the most common way organic molecules are drawn in organic chemistry courses. Being able to interpret and draw line structures is critical to your success in organic chemistry. Before talking about line structures, let us first discuss organic molecules in general. First, some basic facts about organic chemistry and organic molecules in particular. Organic molecules are comprised primarily of carbon and hydrogen atoms. However, they are not comprised exclusively of carbon and hydrogen. Remember that heteroatoms are non-metallic, non-carbon, non-hydrogen atoms. Common heteroatoms that appear in organic molecules include nitrogen, oxygen, and the halogens. Other heteroatoms, such as sulfur and phosphorus, do appear in organic molecules, but will not be common in this course. One of the most important skills you will acquire when beginning to learn organic chemistry is how to draw and interpret organic molecule structures. Molecular structures are how we show what atoms are connected to what other atoms. If you are concurrently taking Chem 232, you will be discussing this topic there as well. So think of this as studying the same material for two different courses. To begin, let me draw you a molecule called 3-butene-1-ol. You don't need to know anything about this molecule, you don't need to know why it's called that or memorize the structure. I'm simply using it as an example. When drawing a structure, you have to show what atoms are present. In this case, I'm going to start with this carbon, and then you also have to show what is connected to those atoms. These lines you see me drawing between that C, which stands for carbon, and that H, which stands for hydrogen, is a bond. I'm now going to draw another bond from this carbon to an adjacent carbon, but this time I'm going to add a second line. That second line is also a bond. This is a double bond, which hopefully you remember from general chemistry. The carbon-hydrogen bonds are single bonds, and the carbon-carbon bond I have drawn here is a double bond. I'm going to continue drawing this molecule. And there we go, that is 3-butene-1-ol. You can see that I have 4 carbons present in this molecule, right down the middle. Remember the Octet Rule from general chemistry. In organic chemistry, the most common atoms you will find are carbon, nitrogen, oxygen, and hydrogen. Carbon, nitrogen, and oxygen are all second-row elements, which must follow the Octet Rule. Notice how every carbon in this molecule follows the Octet Rule. Now let us look briefly at the oxygen. If you look at the oxygen, what I have drawn, that oxygen only has 2 bonds. Therefore, it's not following the Octet Rule, right? Well, not quite. Also remember that atoms can have lone pairs, and that's what this oxygen possesses. Now we can see that this oxygen is also following the Octet Rule. What I have drawn here is a structure that corresponds to 3-butene-1-ol. However, this is not how most organic chemists would draw the structure. How most organic chemists would draw the structure is what I will draw on the right. And I'm done. Now compare how long it took me to draw the structure on the right to how long it took me to draw the structure on the left. The structure on the right is what we call a line structure. And as you can see, the line structure is comprised mostly of lines. Now, how does the line structure on the right correlate to the structure I originally drew on the left? When drawing or interpreting a line structure, there are a few rules you need to be aware of. Located at the intersections, corners, or vertices, whatever word you prefer, of a line structure, you will find carbon atoms. That means this atom on the left, which I am circling in red, is a carbon atom. This corner next door is a carbon atom, and I'm going to continue down the line structure, putting a red dot over all of the carbon atoms. Do you see how these carbon atoms correlate to the structure I drew on the left? Or this carbon atom on the farthest left is that carbon atom. Notice how this has a C double bond. This also has the carbon double bond. And then as we go from left to right, you see how these carbon atoms correlate to the structure on the left. So rule number 1 of line structures: every intersection, every corner, every vertex corresponds to a carbon atom. Now let's move on to the second rule. Maybe you have already recognized that these lines that connect the carbon atoms correspond to the bonds, where this line, which I am overlaying in blue, is a bond, this other line is a bond, and this line is a bond, and so on. And you can see how that carbon-carbon double bond had 2 lines, didn't it? Where I have a second line denoting that double bond. So in a line structure, every line corresponds to a bond. If you have 2 lines, you have a double bond. If there are 3 lines, you would have a triple bond. You may have noticed how the line structure is significantly less cluttered than the original structure I drew on the left. This is because we have not drawn in the hydrogens. In a line structure, the hydrogens are implicit. They are not drawn, but we know they are present. Let's go ahead and draw in the implicit hydrogens in this line structure. Hopefully you can see how these hydrogens in the line structure map on to the hydrogens in the original structure on the left. You can see this carbon here on the left had 2 hydrogens attached to it, and this carbon here on the left also has 2 hydrogens attached to it. In a line structure, the hydrogens attached to carbons are generally not drawn. This is to reduce clutter, to make it easier for us to see the rest of the molecule. As you might imagine, as we get to larger and larger molecules, we are going to have larger and larger numbers of hydrogen atoms present. And drawing all those hydrogen atoms is both time-consuming and makes it more difficult for us to see the rest of the molecule. Note how in this line structure, it was only the hydrogens on the carbons that were implicit. The hydrogen attached to the oxygen atom was drawn, as you can see. Hydrogens attached to heteroatoms, that means hydrogens attached to oxygen and nitrogen, most commonly, are always drawn in line structures. The reason that hydrogen atoms attached to heteroatoms are different than hydrogen atoms attached to carbons is because hydrogen atoms attached to heteroatoms are often used in chemical reactions. They're often very important in reaction mechanisms. In contrast, hydrogen atoms attached to carbons are not often used, and so it is usually okay to simply leave those implicit. Also notice how I have not drawn the lone pairs on the oxygen atom. I can do that. I can go ahead and draw in those lone pairs if I wish, but it is not required. You can draw them in. There's nothing wrong with drawing the lone pairs, and in fact, it may be better for you at the start to draw in those lone pairs so you remember that they are present. However, when given a line structure, always remember that heteroatoms have lone pairs, even if they are not already drawn in for you. To recap the basics of line structures, in a line structure, every intersection, every vertex, every corner, whatever description works best for you, corresponds to a carbon atom. You can see that via the red dots on this line structure. Every line connecting one atom to another atom is a bond. More lines means more bonds. 1 line is a single bond, 2 lines is a double bond, 3 lines is a triple bond. In a line structure, the hydrogen atoms attached to carbon atoms are implicit. They are not drawn. That doesn't mean they are not there. The hydrogen atoms are always there because remember, carbon must obey the octet rule. That means if you see a line structure such as you see here on the right, you must remember that if this carbon has only 2 bonds shown, there must be 2 implicit hydrogen atoms present in order to obey the octet rule. Hydrogen atoms attached to heteroatoms such as oxygen and nitrogen are always drawn. Finally, the lone pairs on heteroatoms can be drawn but don't have to be drawn. So if they are not drawn for you, do not forget that they are there. We use line structures instead of drawing the structures like I did on the left because line structures are faster to draw, they have significantly less clutter, and they are more representative of the actual shape of a molecule. On the left, I have drawn all of these bonds at 90-degree angles. However, you know from Vesper theory, which you learn about in general chemistry, that most bonds aren't at 90-degree angles. You may remember that this carbon is sp3 hybridized, therefore it is tetrahedral, and that this carbon here is sp2 hybridized, therefore it is trigonal planar. And you can see how the line structure better reflects that reality, where this carbon, if I draw in that implicit hydrogen, remember this carbon is sp2 hybridized, therefore its molecular geometry is trigonal planar, therefore the bond angle should be 120 degrees. And this line structure indeed shows a 120-degree angle. If you look at the carbon on the right, we know that there are two hydrogens attached. It is sp3 hybridized, therefore it is tetrahedral in geometry. And while these bond angles are not 109.5 degrees, they are closer to that than what we saw here on the left. Now let's get some practice interpreting line structures. On this slide, I have 4 line structures. Let us go ahead and identify the carbon atoms in the line structure in the upper left. Remember that every corner, every intersection in a line structure is a carbon atom, so let's go ahead and find those. One here at the end, one here, and we continue down the line structure. Every one of those dots is a carbon atom. Therefore, there are 6 carbon atoms present in this molecule. What about hydrogen atoms? How many hydrogen atoms are present? Because we are just starting, let's go ahead and draw in the implicit hydrogen atoms to make that counting easier. Look at this carbon farthest left. This carbon has 2 bonds drawn connecting to it. Therefore, to fulfill the octet rule, there must be 2 hydrogens attached. Now let's look at the carbon next door. This carbon has 3 bonds connected to it. 1, 2, and 3. To fulfill the octet rule, this carbon must have 1 hydrogen attached to it. Now let's go over one more. This carbon has 2 bonds already attached to it. Therefore, this must have 2 hydrogens attached to fulfill the octet rule. And as we continue down, we simply follow that same rule until all carbons have fulfilled the octet rule using hydrogen atoms. Notice how this carbon here has no hydrogen atoms attached. That is because it already has 4 bonds. 1, 2, 3, and 4. Therefore, there are no hydrogens attached to this particular carbon. Let's count the number of hydrogens present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 hydrogens present in this line structure. How about double bonds? Are there double bonds present in this molecule? Yes, we see that this carbon-carbon connection here is a double bond. And we see that this carbon-oxygen connection is also a double bond. Remember that every line corresponds to a bond. If there's 1 line, it's a single bond. If there are 2 lines, it's a double bond. Now, what I would like you to do is pause the video and do the same analysis for the remaining 3 structures. Identify how many carbon atoms are present in each line structure and how many hydrogen atoms are present in each line structure. What I suggest you try to do first is identify the number of hydrogen atoms without drawing them in like we did here. An important part of organic chemistry is being able to interpret a line structure without drawing in all of the implicit hydrogens. So go ahead, pause the video for a few minutes and tell me how many carbons are present in each of the remaining line structures and how many hydrogens are present in each of the remaining line structures. Welcome back. Let's see how you did. Let us look at the structure in the upper right. How many carbon atoms do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. How about hydrogen atoms? Let's go ahead and draw those in just for this one. I have 1 hydrogen attached to this carbon. Why only 1 hydrogen? Well, let's look at that carbon. We have 1 bond, 2 bonds, 3 bonds. Therefore, this carbon needs only 1 hydrogen to fulfill the octet rule. And that's the same for all these other carbons on this side of the molecule. What about these carbons in the middle? How many bonds do those have? 1, 2, 3, and 4. These carbons in the middle already have 4 bonds, therefore they have no hydrogens attached to them. And if we go around the ring, we see that each of the remaining carbons has 2 hydrogens attached to them. And if we count them, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens on this molecule. Now let's look at the structure in the bottom left. I see 4 carbons, and I see 8 hydrogens. If you only counted 6 hydrogen atoms, don't forget to include the hydrogen atoms attached to the heteroatoms. Those are also present. They are important to count. If we go to the structure in the bottom right, I see 6 carbon atoms and 15 hydrogen atoms. If your numbers don't match mine, go ahead and draw in the implicit hydrogens and count again. Hopefully this section has been good practice for you in learning how to interpret line structures. That brings us to the end of this webcast. To recap, line structures are an efficient way to draw organic molecules. As most atoms in organic molecules are second-row elements, most atoms obey the octet rule. In a line structure, each vertex or corner corresponds to a carbon atom. Each line corresponds to a bond. Because carbon follows the octet rule, each carbon atom with fewer than 4 explicitly drawn bonds must be connected to implicit hydrogen atoms. The number of hydrogen atoms connected to each carbon is the number needed to get that carbon atom up to a full octet, or in other words, 4 bonds total.